Hello, good morning. My name is Desai Daniel John, and today I'll be talking about a neural networking model that I made to predict cracks in concrete pictures. Um, for this, before I start explaining what the code is about, I will be training my model because I'm going to be training it for 50 epochs, and this will take some time. So let me get the training started while I brief you on the code thus far. So for this model, I made use of the following libraries. From NumPy I imported NP, from PIL I imported image, from I also imported OLs from Skitlearn model, Sidekick I imported training, and as follows. And also I made use of the TensorFlow neural networking, the TensorFlow library. Um, After importing all these libraries, as you can see here, after importing all this library, I had to the first thing I did was to define the size of my image, of which I set the size to be 224 by 224. This is a matter of choice. You can set it to 225, or whichever one you're really interested in. So I set mine to 224 pixel by 224 by 224. This is the length and the width. And then I passed it, and I also set the image channel to 3, which is the red, blue, green. These are the three primary colors that can be mixed to get any other color that my image would have. Um, for this project, this project, the study area was Lamar University. I went around campus and I took pictures of cracks on road pavements and also pictures with no cracks. And after doing that, in the pictures that had the cracks, I saved them in the positive, and the ones with no cracks, I saved them in the negative file. So here we see that I imported the library and I saved it in the positive dir and negative dir. So these are where my images are saved. And after that, I had to define a function to read and process the image. So here we have to define a function to read and process the image, and we use the PIL library to do this, and we also use the NumPy library to also convert it back to what the model can work with. So in image, I from the file path, which is the file path that I set here, I saved an image. So and in image array, after converting it, I had to save it in image array, which is just a different object. And then after that, I loaded the positive images, which is what is happening here. For most of my pictures were in JPEG. I included this just in case because I used another set of cameras, and I didn't really want to I didn't want to go through it and see if they were all in JPEG or if some were in PNG, so I just included that just to be sure, and so I wouldn't come up with any problem as I go. Then I also did the same thing too for the negative image, for the image without cracks, which is the negative images. Then we have to combine these two objects together to form to become one data set, which we save in the end. For this, we use the NumPy library and the NumPy library with the help of an np.concatenate function to bring these two data sets together and form just one data set. Then also we this is for the x variable, and we also need a y variable. For the y variable, we have to assign for the positive images, we assign the value of 1. For the negative images, we assign the value of 0, and then we put that we create another object and name that object y. Also combine two, and then we have to shuffle these two objects so that we have a well distributed well distribution of our data set, so that it's in this case, because initially what the data set will look like is that maybe from the beginning to maybe from the image 1 to probably our image 100 or 120, whichever one we have, it's going to just be showing maybe non-crack first and then later on crack, but we don't want that. We want everything to be well mixed. So that is why we have to shuffle it. Then after we shuffle it, then we do a split string and I set the random state to 42. You really and I set the random state to 42, which really doesn't matter. You can set it to any other random state that you please. But I use the random state of 42. I'm used to it already. And but for this data set, I used 20% of the entire data set for testing and the remaining 80 for training. The reason why I did this was because of the size of my data set. I think I have about in total I should have about 300 and something pictures because I had to take out some pictures that had some features that I didn't want. So I had to take those pictures out. So I ended up with about 300 and something pictures in total, 345 pictures in total. So I had to use just 20% of it to test, and I needed to use the remaining 80 for training. And why I used the remaining 80 was because I need to still split the training set into training and validation. So I still wanted to have a good number of images to train my model on. So after splitting into training and testing, I also further split into training and validation, which I took 20%. And if we see here, we can see for the training data set, let me run this so that we can see the sizes of what are in each of this. I think the model should be done training by now. Yeah, it's done training by now. So here we have 220 in our training set, and we have 56 in our validation set. This validation set we use in setting our hyperparameters. And and in the testing we have 69. So after this, then we now define the architecture of our model. There are 8 layers in this model. The first 3 layers are convolutional layers with 32, 64, and 128 filters respectively, with filter size of 3 by 3 as we can see here, and has a ReLU activation function. The next 3 layers are a max polling layer with pool size of 2 by 2. Then we have the flatten layer, which is used to convert the output from the convolutional layer to a one-dimensional vector. And then the next layer is the fully connected dense layer with 512 units and a ReLU activation function. Then we also added a dropout, and we made a dropout of 0.5%, which is to drop out 0.5% of the lowest weights randomly. This is just to ensure that our model is not overfitted. After defining the architecture of the model, we now further go in, we can now compile the model. Then we train the model for 50 data sets. That's why I did it initially, so it doesn't take too much time. Now the model is fully trained, and we can see from here after the training we got an accuracy of 0.96, which is about 96% accuracy. We can also still run this just to check, so we can see testing set accuracy. On the testing set, this is the accuracy that it gets on the testing set after we have run the model. And then now we can make predictions, and for me to be able to view these predictions better, I had to plot a confusion matrix to do this so that I can have a better picture of how the model performed. Sorry, that was a mistake. I'm supposed to run it up to here in the CM. Yes, now that works perfectly. So let us see the plot and see how the model did. Obviously the model is not gonna be perfect, but then again we just want to see how successful we were. So here now we have 27 cases in the top left corner here where the model predicted negative and the actual negative, and we have 25 instances where it had cracks and the model actually said it had cracks. We have 3 cases where it was actually no cracks, but our model said there were cracks, and there are 14 cases where it had cracks, but our model said no cracks. And this is how the neural networking this is how my neural networking model did, and this will be the end of my video. Thank you very much. Till next time.